I once again welcome you, wish you a very good evening and welcome you all to the 12th lecture in the webinar series that is being organized and hosted by the Archaeological Sciences Center. We are situated in the Indian Institute of Technology, Gandhinagar. As you all know, we have been conducting this webinar series for the last 12 months. So with this lecture today, we complete a year. And we will definitely be continuing for many more months. So please stay with us. Please do join us every month for this for these monthly series. And so far in the talks that we have held till now, we have covered many topics in prehistory and proto-history. And hopefully from the next month onwards, we will be moving on to several other cultural periods of India's ancient history and archaeology. And maybe one or two lectures will be an exception where we may go back to prehistory or proto-history, but we will definitely be moving forward in terms of cultures and time periods. So today we have with us very aptly Professor Michel Danino, a very eminent scholar, and he's also the visiting professor in the discipline of Humanities and Social Sciences at IIT Gandhinagar. He's also the coordinator for the Archaeological Sciences Center. And most of us know him very well, and we are aware of his contributions. But I would still like to give a short introduction, and especially for those participants who are new to this, the topic of this talk, or to Professor Danino. Well, he has authored several books on Indian civilization, including the most popular, important ones like The Lost River on the Trail of the Sarasvati and Indian Culture and India's Future, apart from many research papers on Harappan metrology, town planning, the Sarasvati River, the Aryan debate, and several other cultural issues. He was a member of the Indian Council of Historical Research and is the convener of the Central Board of Secondary Education CBSE committee for the course Knowledge Tradition. Textbooks that he co-edited with Professor Kapil Kapoor are available. And in 2017, the Government of India conferred and awarded him the Padma Shri for his work on education and culture. And very recently, we were happy to know that he has been selected as a member of the National Steering Committee for the development of national curriculum frameworks. So with this introduction, I welcome Professor Danino and I pass the mic on to him.
Thank you, Sharada. So thanks for this kind introduction. I hope I'm audible to all. And today I would like to take you on a small journey through Harappan Town Planning, which initially seemed a little boring to some of the Western archaeologists. In fact, I think it was Mortimer Wheeler in the 1940s who complained about the endless miles of monotonous bricks in Mohenjo-daro and Harappa. Because you see, there were no pyramids like in Egypt, there were no colossal temples, there were no royal tombs with a lot of treasures, etc., etc. So it seemed like a very pragmatic civilization with limited art production and basically a civilization of craftsmen and traders above everything else. But this is a picture which has changed a lot in the last decades because a number of unusual features have come to light. And beginning with the way in which it was governed. I will not go into this. I believe Dr. Prabhakar addressed this issue in his talk recently. This is unlike other civilizations for the simple fact that there is apparently no military order and no obvious sign of warfare. So how this whole civilization hang together and click together is still something of a mystery. But what is certain is that all across this huge region, from, as you all know, from what is today Afghanistan to northern Maharashtra, In the east, the Iranian border, all the way to Western Uttar Pradesh. It's a huge expanse. And even though there are considerable regional variations in every feature, whether you look at pottery, whether you look at figurines, religious artifacts, and so on, nevertheless, there is also a kind of sharing of very important central concepts. And archaeologists speak of standardization. It is visible, especially in things like the series of weights and certain urban features. But definitely there is a sharing. Who decided on these concepts, who agreed that they are going to be shared and adopted in all the regions. These are questions that may never have an answer. But meantime, today, I will take you through certain unusual features of town planning, which I've called unexpected, in fact, because they came to light only recently, and they are the least conspicuous, yet they seem to have had considerable importance for the Harappan town planners, architects, and perhaps for the population at large. That is, of course, more difficult to say. So let me start this journey. This is, of course, a view of the East Reservoir with the castle of Dholavira in the background. We will return to this very shortly. So first of all, let us separate two issues. One is that we are going to discover a very systematic use of proportions, ratios, in almost every major structure or feature of the Harappan town planning. This is unexpected, and it is, what archaeologists sometimes call a non-utilitarian feature. I'll not develop this terminology, but it's just that, today's architects, for example, would not be bothered about the use of specific proportions and ratios, and yet the Harappans were. So apparently they don't serve any visible purpose, so they are labeled as non-utilitarian, but nevertheless, they were quite concerned with this, and therefore there was a certain cultural importance attached to these ratios. So initially, and I'm going to separate this from the question of linear dimensions, which I will address later in the second part of this talk. So first of all, something which was noticed very early on, and this is the upper city of Mohenjo-daro, also called Acropolis, sometimes called citadel in the literature, but citadel is a military term, in fact, and therefore immediately introduces a certain framework of interpretation, which I will avoid, and I will use neutral terms like Acropolis, upper city, and lower city in some cases, and so on. So here you see, if I use my pointer, you can see some famous structures like the Great Bath here, the so-called granary, so-called because there's no final evidence that it ever was a granary, and more of them like the pillared hall, which is going to be here, which we will revisit, and more structures. So this was not an area which was used for common habitations. These were localized in the lower town, which is very extensive in Mohenjo-daro. The final surface area of this city is still unknown, but it was certainly at least 200 hectares, if not much more. And what was noticed earlier was that this Acropolis was twice as long as it was wide. All right, so this is simple enough, and it doesn't take us very far. However, the picture gets more interesting when we find this proportion repeated at other sites. And one of them is Kalimangan, excavated in the 1960s by Professor Bibilal, to whom, in fact, I would like to dedicate this talk. He is 100 years this year and still thinking about archaeology and writing about archaeology. And he, along with B.K. Thapar, directed the excavations on behalf of Archaeological Survey of India in this city of Kalimangan, which is not very far from what is today the Indo-Pakistan border. So here you see that we have also a division between upper and lower cities. So this is a shared feature of urban town planning. And this we're going to see repeated in quite a few other sites. And we see that the Acropolis, which is on the left, on the western side, is also divided into two more or less equal parts, but the proportions are 1:2 or 2:1, as you like. And this is here repeated in the fortified lower city, whereas in Mohenjo-daro we do not have such dimensions. In fact, very few fortifications have survived in Mohenjo-daro, but here they were traced and we have a similar proportion again. So something is going on, but let us proceed. And let us come now to Dholavira, where I'm going to spend most of the time of this presentation in the Rann of Kutch. And I'll not spend too much time describing Dholavira because Dr. Prabhakar did it last month on the occasion of the UNESCO nomination of this site as World Heritage Site. So this site was discovered in the late 1960s by Jagatpati Joshi and excavated in the late 1980s, 1990s, and early 2000s under the direction of Dr. R.S. Bisht. And we see that here we do not have a dual division, a twofold division between upper and lower. We have a threefold division between upper. This is, I added some color to make it more conspicuous. And we see again a division into two almost equal halves. So that is again a shared concept. But here we have a middle town and a lower town in addition. And obviously very pragmatic considerations such as the availability of rainwater flowing seasonally in these two nallas, the Mansar and the Manhar, and the need for the city to harvest this water must have dictated certain considerations different from the environmental context of, for example, Mohenjo-daro or Kalimangan. So here we see that luckily the fortified enclosures broadly survived because the foundations were made of stone, and therefore we are able to draw an almost complete city plan, which is not often the case in Harappan urbanism. Now, after measuring these main dimensions, so we have the upper city here at the bottom, consisting of the so-called castle. This is the eastern part of it, which has very thick fortifications, and it was christened castle by Dr. Bish. On the western part of this upper town was the bailey, so-called bailey, then the middle town, and then the lower town. And those dimensions were very precisely measured by Archaeological Survey of India and recently confirmed by not only some GPS studies, but also by a complete drone survey of which actually our center here at IIT Gandhinagar conducted on behalf of Archaeological Survey of India. So now these dimensions are there, but then certain strange things are beginning to happen. And these were first noticed by Dr. Bisht. And he noticed that the proportions of the length to the width of these structures in the castle, both inner and outer, the bailey, the middle town, the ceremonial ground, which is just between, as you might have noticed, just between the castle and the middle town, and the entire city itself, those proportions between length and breadth were not random. They were fixed to very simple ratios, like, of course, 1:1, that is a square, but 6:1 for the ceremonial ground, 5:4 for the castle, as well as for the entire city. And please note the very low margins of error. For example, for the entire city, and that's 771 meters long, over an irregular terrain in addition, the margin of error of this ratio is 0.001%. So if you round it off, it's 0%. So incredible accuracy, which rules out mere coincidence, because if it was mere coincidence, we would have bigger margins of error. And apart from the outer castle, but then we know that the castle went through certain complex phases of reconstruction and additions and so on. So it has a complex history. But apart from it, all margins of error are within 1%, which is very precise, considering also that in 4,500 years approximately, there could have been displacements due to erosion, due to some alterations happening in the structures by natural phenomena, including earthquakes. So it is a remarkable degree of precision. But to these ratios, I added, after conducting some research based on all those dimensions, I added many more. And I'm going, instead of reading out this table, which will be a bit cumbersome, I'm going to show them to you on a plan. And here also you see that the margins of errors are very small. If you average all the margins of errors, you come to about 0.6%, much below 1% on average. So there is something going on. And this was a plan, in fact, which Dr. Bish drew. It has been redrawn for the UNESCO report, where in addition, he pointed to all these dimensions and ratios, but in addition, he also pointed to the fact that if you take the two diagonals of the overall town, they intersect precisely in a way that will touch the two edges of the castle. So is it a deliberate initial design, or is it a consequence of other geometrical choices? That is a question I address in a separate paper, but I will keep it out of discussion for today because it will take us to the entire evolution of the city in different stages. I wrote once a paper on this, and I will leave it at that for the time being. So let us now see, back on the plan, those ratios. This is the castle on the eastern part of the Acropolis in blue, and the ratio is 5:4, both inside and outside. And again, for the overall city, 5:4 is repeated. Now we have also a repetition of 9:4, but keep in mind for a later discussion that 9:4 is nothing but 5:4 plus 1. 5:4 is 1.25. Divide 5 by 4, you get 1.25. 9:4 is 2.25. So there may be something there. I will come to that later. So here is between the length of the castle and the length of the middle town, you have this ratio of 9:4. And it is repeated, which it did not have been, between the length of the overall city and the length of the middle town, right? So this continues. We have 6:1 for the ceremonial ground in green here, and 7:6 for the overall middle town. Right. So now let us proceed further. So this is another way of drawing the proportions to adjust in case it was not clear enough. And you can also add 1:1 for the bailey, which is an almost perfect square, whereas the castle is deliberately not a square. Now, it's not limited to those overall major structures. When we look at the reservoirs, and Dholavira has many reservoirs, maybe there were even many more, which were like earthen reservoirs, but constructed or rock-cut reservoirs, there are at least 6 of them. The major east or eastern reservoir, which I'll show you a little later, and then the 5 reservoirs on the southern edge of the castle. But I've put an asterisk where those reservoirs were not very well defined. For those which are well defined, again, we find certain simple proportions, simple ratios with low margins of errors, as you can see, 0.3%, for example, for the east reservoirs. And for those which are ill-defined, expectedly, we find slightly bigger margins of error. So what does this mean? And this is, again, the east reservoir, and this is the 5:2. or otherwise, or in other words, the length is 2.5 times the width, and with a very low margin of error. This is definitely a pattern building up. And this is the rock cut reservoirs on the southern side. It is called SR3, and this SR3 has a proportion of 7:2, while it has a secondary rock cut reservoir carved out at the bottom, perhaps to augment its capacity or for some other purpose, which I do not know whether Dr. Bish has ever proposed an explanation. But anyway, we are happy to note that it also obeys a very precise proportion. This is 11:4. And here it's very easy to measure because it's rock cut and it would not have budged in the course of time. So therefore, there is a pattern building up. The pattern is repeated in the castle itself, where we see, this is from, I borrow this from ASI, we see that if this is a kind of Broadway, as I believe Dr. Bish calls it or nicknames it, which crosses from east to west the entire castle almost, and the upper part is 3 times as broad, while the lower part is 4 times as broad. So this division also, inner division of the castle is something unexpected. There is a northern gate here, and it's the length of the sentinel room, we will revisit it later, is twice the width. So there is again a passage. So this can be codified as you can see here. 1 for the Broadway, 3 for the upper part, 4 for the lower part. And this is a closer look at the, I'm sorry, this was a work in progress, not final. So let me now move on to other sites, because what about, why stop at Dholavira? And we see that other sites also display a lot of ratios and with very high degree of precision again. So this is the so-called Granary of Harappa. I say so-called because again, there is no evidence. And in fact, there's a growing opinion among archaeologists such as Professor Kenoya that it need not have been a granary at all. Maybe it had some completely different purpose, which we don't know. But this is one of the largest structure in the entire Harappan civilization. And it happens to be more than 50 meters in length, which is very huge. And it's the ratio between the length and the width, as you can see here, is almost exactly 1.25. That's the same 5:4 that we have encountered at Dholavira. And there are 6 inner chambers like this one, and their ratio is 5:2, which we already saw at the East Reservoir at Dholavira. So I will now increase the pace because there is no point stopping at every single structure. But if you revisit the Acropolis of Mohenjo-daro, which I showed you earlier, you find that every single major structure obeys a simple ratio. And I've included here the margins of error. In fact, the Great Bath itself, the whole structure of the Great Bath itself is based on 3 ratios, 5:3, 7:5, and 7:4. And this goes on. This is in the lower town of Mohenjo-daro, a major building, which has been variously interpreted by the archaeologists. I will not go into the various designations it has received. Several schools of thought think that it was a kind of a temple, but it's not easy to prove. So what is of interest to us is that if you take the central points of the width and the length, again, you get almost exactly the same 5:4 ratio. So now we're beginning to feel, and it's again at Lotal, a small site in Gujarat, about 80 kilometers south of our IIT Gandhinagar, you find that again, if you take the middle point here, of the width and you take the length, you will get the same ratio of 5:4. Whereas the dockyard is 6:1, and 6:1 we have encountered again in the ceremonial ground of Dholavira. So this builds up further, and this is a view of the Lotal dockyard. And now to sum up the whole picture, I drew this map and I added a few more of all the major structures for which precise dimensions are available, because sometimes they are not available, and we find that all of them can be pegged to a simple fraction, a simple ratio. Now, we might object that it is always possible to find a fraction close to any dimension. Yes, we can always mathematically find a fraction close to any number that you give me, but the fraction may not be a simple one. And here I insist that we are dealing with this one exception of 11:4, and I'll discuss it a little later. We are dealing with very simple ratios. So that is not a random distribution. It is deliberately a pattern. So why is that? We now have to, since we do not have Harappan literature, we have to look at classical Indian architecture, which is called Vastu Shastra, Vastu Vidya, and so on. It has Shilpa Shastra and so on. And there we find some clues. And of course, I'm not going to claim that Vastu Shastra existed in Harappan times, but we cannot rule out, since there is a very considerable Harappan legacy in a number of spheres from technology to religion, we cannot rule out that some seeds of certain concepts may have been transmitted from Harappan times. Now, if I look at a text like the Brihad Samhita of Varahamira, it's a kind of encyclopedia of the 6th century AD or CE, we find that there is an indication on auspicious dimensions. There are 2 chapters in it dedicated to architecture. And Varahamira says that for auspicious dimensions, if you look at the palace of the king, so it's very interesting that this is addressed to the ruler. You have to make the length equal to the breadth plus 1/4, 1/4 of the breadth. So 1 plus 1/4 is 5/4. That is associated with the ruler. And it's interesting that it was there in the castle in Dholavira, where expectedly the rulers would have resided. And the length of the house of the Senapati, the commander-in-chief, you will get a ratio of 7/6. But it is even more than that, because if you take other texts, like the Manasara, for example, they make it very systematic, and they give us a process which the Harappans may have followed for the simple reason that this process does not require any mathematical knowledge of fractions or ratios. What is done here is simply to build a series of mansions, residences, rooms, with a series of fractions. And what you do is that you always start with the width, and you add to this width, and I added the result in square brackets in this quotation. You add to the width a fraction of it. So either 1/4 or 1/2 or 3/4, or the same width, breadth again, or greater than twice by 1/4, etc., etc. And you are getting here all the proportions that we saw at Dholavira, including this 11/4, which apparently was not such a simple fraction. So this is remarkable that in this single shloka, if it is a shloka, I forget, in this single verse of Manasara, you get all the major proportions that were noticed at Dholavira, along with the process of how they can be very simply made without any particular, once you have decided on a breadth, you can extend a rope, fold it into 2, and you can add the half, or fold it into 3, and you can add a third. You do not have to know anything about fractions particularly. So this is something which I think gives us a strong clue of some continuity in fractions or special ratios, proportions. But now we know in this historical classical context that these proportions, these ratios were attributed a certain quality of auspiciousness or even sometimes sacredness when we are in the context of temple construction. So we cannot, of course, in retrospect, apply this backward to the Harappan town planners, but why should they have bothered so much about imposing in almost every site where we get dimensions these proportions if they do not have a strong cultural meaning for them? So I believe it is not too far-fetched to at least keep the concept of auspiciousness. Sacredness, we don't know. But there was something which for them was very attractive about these fractions. So that's a little bit of what might be called cognitive archaeology if we try to read the mind of the Harappans. Now, continuing even before classical India, in fact, we can see the root in the Vedic literature. So whether that is connected with the Harappan or disconnected, independent, I'm not going to go into. This is a whole different topic altogether. But we see in texts of like the Brahmanas, which depict the construction of sacred altars, we see some of these proportions already taking place, which of course will be transmitted in the later literature and classical period. And this very important Mahavedi, which is the fundamental ground plan for the Vedic, the complete Vedic sacrifice in for example, the Shatapatha Brahmana. The sacrifice is going to take place here on the western part of the sacrificial ground, but there are a number of altars here on the eastern part, and this sacrificial ground, strangely, instead of being rectangular, is trapezoid with a proportion of 1.25. These are the units given in the text. I've not made up anything, and we find the same 5:4 here again. So this 5:4 here in the Vedic philosophy can be understood as a growth. It represents the growth from the eastern dimension here to the western dimension. It symbolizes the growth of the sacrifice, because all sacrifice in Vedic philosophy is about growth, whether inner spiritual growth or outer growth, acquisition of more wealth and so on. That is a matter of interpretation or situation. But there is no doubt that especially this 5:4, this 1.25 is seen as a very auspicious proportion in the Vedic and later classical philosophy. So here is a reminder, but I would like to add to this that this survives even in popular culture in India, where, for example, there is a concept of sawaya, and sawa in Hindi is actually 1.25. It is one of the fractions that Hindi commonly uses, but it is something which is used in Hindu temples even today. In some temples, if you want to make an offering of 1 kilogram of rice, for example, you will be told to offer 1.25 sawa instead of 1 kilo. It is regarded as more auspicious. If you take the ruler Jai Singh, who constructed the Jantar Mantas, for example, he had an additional title stuck to him, which is Savai Jai Singh. And this means 1.25 Jai Singh. It simply means that he is said to be, 25% greater than his predecessor. It is one way of putting it. So it's a modest increase. It's not, hyperbolic self-praise, but it is also about growth. And because otherwise, how do you explain, that a ruler should call himself 1.25 somebody? So this is this concept which auspiciousness and growth, which we can understand from the classical period, whether we can apply them back to Harappan times, of course, will be somewhat speculative, but to an extent, I believe we can. Now, this is the first part of the question, and I think largely it is not controversial in the sense that certainly the Harappans used those ratios and were almost obsessed by them because they replicated them in a lot of sites. But I wanted to go a little further, and I started from a simple hypothesis that to apply a dimension for a room or a house is not very difficult. You don't need any unit. You just take the breadth of your house, as you know, as the Manasara text told us. You can have a rope, and you can fold it into two and add it for the length. You don't really need a unit. But I believe that in Dholavira, to get this degree of 0% margin of error for the entire city, a simple rope will not do. You need a unit to guide you and to measure out on the land, to measure out the whole dimensions. So I started with a problem. Can we measure, can we identify a particular unit? And I started with two assumptions. One, that there was such a unit, and that they did not just measure out things with their steps, as some archaeologists have assumed. In fact, there is Professor Kenoya, in fact, himself has advocated the use of hand spans and cubits and steps. And of course, all of that would have been used. But he objected to the concept of a specific unit of length, which is hard to understand when contemporary civilizations, like the Mesopotamian, the Egyptians, had extensive systems of linear units, weight units, volume units, and so on. So anyway, let us assume that there is such a unit. And the hypothesis, the key hypothesis is going to be that as much as possible, we should expect most of the major dimensions to be integral multiples of that unit. That means they should be 3 times, 4 times, 20 times, but not 3.71 times, because then, of course, it becomes meaningless for us. And if these proportions were so important and were measured out by a unit, we would expect that maybe not all, but at least a majority of situations would see these integral multiples. So n times u. And then the problem is, what is the largest unit in terms of length, in terms of which most of Dholavira's dimensions can be expressed as integers. And I'm going to make it very simple because it's just a basic problem of class 8 level of mathematics, or even maybe class 7, I'm not sure, where I define all the dimensions and I use all the ratios, which we have seen, to express the dimensions in terms of each other. And then I simply come to a situation where I can take the LCM, the least common multiple of all the factors I have worked out. These are very basic multiplications and divisions. And I find that, yes, there is an n, which will allow us to express all these numbers in terms of integral multiples. Integral, these are not fractional multiples of this unit, which happens to be 1.9 meter. Now, I call it D, no longer U, but D for Dholavira. And I say that this unit allows us to express all these dimensions in multiples of itself. Now, you can see those numbers. Interestingly, there are numbers of multiples of 10. We have 10 here for the thickness of the castle, 19 meters maximum thickness of the castle fortification. We have 60 inside, we have 80 outside, 150 for the overall ceremonial ground, 180. So there's a great regularity in having so many unexpected multiples of 10. But that is not sufficient. Let us proceed. And first of all, let us say, because maybe you think that I have duped you by just putting these numbers of a plan, but no, if you compare now the actual measurement in terms of keeping those numbers here with one which is not an integral multiples, and it cannot be because we have a ratio of 7:6 for the middle term. 7:6 will not give us a perfect integer for both dimensions. One of them is going to be fractional, expectedly. But when I multiply now the actual measurement by or I compare, let us say, the theoretical measurement, which consists of the length, these units multiplied by the value of d, by 1.9 meters, I come to a certain theoretical measurement, but there is the actual measurement on the ground, and I can compare both. And when I compare both, I find again that the margin of error is extremely small. And except again for the outer wall of the castle, we have very negligible margins of error. So these numbers work well. But is that all we can say? And if I come now to I come back to the castle, properly speaking, I can now express the main dimensions in terms of 3 times this unit of 1.9 meters, 9 times, and 12 times. So here there is a little bit of larger margin of error. We are around 2%. But then we know also that the castle has gone through many phases of readjustments. So it's not very surprising. Now, can I produce some statistical method to justify that this is the best unit? It came as a simple LCM calculation, but could there not be a better unit which would account for all these dimensions? So very briefly here, and I will not take much time, I would like to explain how I did with the guidance of several experts. I should name here Professor Aryan, formerly of Indian Institute of Science, Bangalore, now Jain University. I should also acknowledge Professor Muralidharan, a former head of statistics department in MS University, Baroda, and several other people who helped me with these calculations. The first was to test all units, for all possible units, from 30 centimeter to 4 meters. I took a very wide span. And again, all the 22 larger dimensions, 21 smaller dimensions, which I could gather from Dholavira. Now, I would have to add more to this because we have the drone survey. So we have now a new phase beginning where we can take more measurements and test this method. And here, very simply, we calculate the remainder. Suppose I have a dimension somewhere. I will suppose that this dimension was measured out by all these units, either 31 centimeter or 32 or 33. And I would expect that for the best candidates, the remainder that I should get should be as low as possible. Like if you have a table measuring 1.8 meters and you are testing it for 60 centimeters, you have zero remainder. Okay, it is 3 times a possible unit of 60 centimeters. But if you try 63 centimeters, it's not going to work well. You will have a higher remainder. So it's a very simple spreadsheet which gave us all the candidates, and I'm only taking a small portion of it because this is where I get the best candidates. And we see that we have several good candidates, especially, so the more interesting, I'm listing them here, 1.7 meters, 1.39, 1.8, 1.9. I'll show you why I'm focusing on 1.84 and 1.9. The best here is 1.84. It works better with all these dimensions than 1.9 meters. So let's continue. And this is what happens. You see, from 30 centimeters all the way to 4 meters, I could not, of course, squeeze. If I do that, then it'll be unreadable. But all the way to 4 meters, we got all this graph where we see that, of course, the smaller the unit, and the best things are going to work. Because if I take a unit of 1 centimeter, then I'm going to have a zero remainder for all dimensions because all dimensions are expressed in terms of centimeters. So the smaller the unit, the smaller the remainders are going to be. But remember, I'm looking for the largest unit, which will make sense of all the dimensions. So this is 1.7, this is 1. So statistically, these are called pits or minima, where the deviation is minimal. So you can see that in this whole landscape, there's another one here, around 1.17 meters, you see that there are some candidates. And what I did was simply to list them objectively. Then there was a second method where we express the dimension in terms of the nearest integral multiple of any tested unit. So I say, for example, that I have again 60 centimeters, and it gives me 1.8 meters, and I say that this dimension is that much away from that particular nearest integral multiple. It's mathematically, it's a difference, a different kind of test, and then we can express the difference in terms of percentage. Do I deviate by 0%, by 10%, by 50%, and so on? So here we have, and the proof that this is a different method is that we are getting different candidates. And for example, 1.26, 1.7 meters now are good candidates. But we find that 1.84 is no longer such a good candidate. 1.9 meters in this test is actually a better one. So this is the curve here, and you can see how it works. So we have, of course, a lot of other candidates, but remember, we are interested in the larger units. So we're interested in something in this, because otherwise beyond the deviations become too considerable. And the last is imposing a threshold. Imposing a threshold means that we say, look, I'm not going to consider any unit which gives me average deviations above 1%. I consider, and this is actually what I chose, 1%. I consider that above 1%, it's not a good candidate. And I will rule out those which are above the threshold. So here we have a certain score for all the units, and what is the score that unit after unit that is going to be implemented. And we find that here the higher score, the better. In other words, when there is a threshold below 1% for the dimensions, we attribute 1 point. So for 24 dimensions, 1 point, the unit of 1.9 meters is below 1% deviation, whereas 1.4 is only for 17 units. So if you see the graph, to cut a long story short again, here, this is the threshold study. And you see that here, this is about scoring. So the higher the score for the dimensions, and the better the unit. So of course, we have a smaller unit here, and it's not surprisingly, it is just half of 1.9 meters. And obviously, if 1.9 meters is going to be a good unit, half of it, quarter of it, 1/10 of it are going to be even better units, you see, because we are looking for integral multiples. So this all makes sense. And altogether, this is a statistical confirmation that 1.9 meters performs better overall than 1.8. And I'm finally producing some circumstantial evidence, as I call it, of occurrences of direct occurrences of 1.9 meters in Dholavira. These are two columns which have been variously interpreted in within the Broadway of the castle. So the castle starts here on the eastern point and moves to the west. And these columns, well, again, I'm not bothered about the interpretation, where they erected for, but the dimensions is very precisely 3.8 meters. And this is, and I'm taking the ASI dimensions always. So this is exactly twice our unit. There is an underground chamber within a radial funerary structure, and Dr. Prabhakar spoke about it last month. And this chamber, which you can see here, it is rectangular. If you look at the dimensions given by Dr. Bisht, the dimensions, I'm sorry, are 1.9 meters, the depth, 1.9 meters, the width, and a suspected 3.8 meters length. It was not fully measurable, but this was Dr. Bisht's estimate. So here we have a very strong backing of the dimension of the tumulus. And this is the east gate of the stadium, which measures again 3.8 meters. And we have more of these. So I'm going to again, cut a long story short. There are blocks of houses in Mohenjo-daro which measure 9.6 by 19.2 very precisely, 4 times and 8 times the dimension, the unit which we have figured out. And I was able to find many structures, for example, in Farmana, where we have a lot of dimensions available in the excavation report. I could find at least a dozen houses which had dimensions in integral multiple of 1.9. But then we had a problem, which is that there are also lots of houses that do not conform to this pattern. And this is, in fact, my conclusion, that we should look at this principle for the larger structures and the larger features. When it comes to domestic houses, there are too many constraints on the ground between two streets or between two existing houses. And you cannot demand that each and every house should be, patterned on this principle of integral multiples of this given unit. It would be just too much to ask. And it might not even be feasible if we wanted to do this. So finally, in a series of studies, Professor Balasubramaniam, the late professor of metallurgy in IIT Kanpur, tried to apply this unit to various historical structures, and we did some of this work together. The Barabar rock cut chambers were giving very good integral multiples of this unit, but he found that this Delhi iron pillar, which is, as some of you might know, a structure consisting of rust-resistant iron, and he's the metallurgist who worked out the full chemical process by which it is able to have survived for 1600 years with almost no rusting. He found that, strangely, if we took the total dimension, including the buried part, and measured it to the emerged height of the pillar, we have a ratio of 5:4. So this is a bit curious, but in addition, he showed that this total dimension is exactly 4 times the Dholavira unit. So is there also a transmission into historical period of the unit itself? This is something that I have tried to address in a few papers, and I will end with a few remarks on a possible subunit of this unit, which would be a kind of Harappan angula. In classical times, the unit is defined as barley grains, mostly, and it has been estimated also the width of the middle finger of an average man. But these are not very strict units. So Varamira gives us something that is better in terms of calculation of the angula, and I'll show it in the next slide. And for practical purposes, British scholars equated the angula to 1/3 of an inch, but I will show that this doesn't work very well, because if you take the natural dimension, and this is something that has been done in classical India, all the dimensions of the human body, like the finger, as I said, the width of the hand, the palm, in other words, the span, the cubit, and so on, have all been very well defined. And this is what Varamira uses here to give us, in terms of angula, the height of a man. And this is, a tall man is 108 angulas, an average man is 96, and a short man is 84. Now, if you take this 3/4 inches, which is about 1.9 centimeter, you're getting dimensions which are not very sensible. An average man is not 182 centimeters. In fact, I've taken here skeletal evidence from anthropological surveys to show that this was about 170 centimeter, and this is confirmed in later historical India also. So when we look at a dimension of 1.76 centimeters, which is the result. I will show you why I'm taking this dimension in particular. We have much more sensible dimensions. Or if you prefer, I could say, let me divide this height of 170 centimeter, which comes from skeletal studies, by 96 angulas, and I'm going to get 101.76 centimeter for the angula. And then do we have any independent evidence that such a unit would have existed in Harappan times? There is some. First of all, this Lotal scale excavated by Dr. S.R. Rao, which is made of ivory or bone, and which point to a unit of all these graduations which you see there are very, very precisely 1.77 millimeters apart. So the metrologist Mainka long ago related this to the Arthashastra angula, which he had identified independently, to 1.778 centimeters. So in other words, 10 Lotal units equal to 1 Arthashastra angula. Apart from that, there is here another scale which was analyzed by Professor Balasubramaniam again, and we had discussed this scale together, which is a rough terracotta scale excavated at Kalimangan. And it might have been this kind of a scale that perhaps a mason, a builder, would copy from some other scale and keep in his pocket, if there were pockets. We're not sure about that, but keep with him for the daily construction. It was in terracotta. If it broke, it would not matter, and he could copy more. I mean, this is just a hypothesis. But when he did the analysis, he found that these grooves were averaging 1.75 centimeters apart. And if you take an average between this 1.75, 1.77 with the Lotal scale, you get to 1.76, which is what Vahramira scale indicated to us. And interestingly, and I'm closing with this, interestingly, Arthashastra tells us that there is a dimension of 108 angulas to be used for the construction of city walls. And this refers to 108 angulas refers to a dhanush. This is, of course, a bow, but this dhanush has several values in Arthashastra. For construction of city walls, which is what we see at Dholavira, it would be 108 angulas. And if we multiply 1.76 by 108, we get exactly 1.9 meters, which is the unit we had independently calculated. So therefore, if this is taken further, and we will need to do more studies with the additional dimensions we can get from a number of sites, this is a work in progress, then we would, whether there was an angula or not, at least we would be able to find a very striking example of legacy of concepts of ratios and proportions in town planning, and possibly of units also. I have tested this angula against a few seals. I didn't want to go into details today for lack of time, but it works for the larger seals quite well. A lot of smaller seals do not seem to be patterned on the angula, but the largest seals seem to have been. So anyway, there is more work to be done, but there is enough data now to assume that both auspicious ratios and linear measures were in practice in the Harappan Town Planning. And some of these concepts and perhaps the dimensions themselves were transmitted to later Gangetic civilization and classical civilization of India. So in brief, this is an outline of the research I've been doing for some time, which I hope to resume soon here at IIT Gandhinagar and supplement and build into a corpus of evidence. Thank you very much.
Thank you, Professor Danino. This was a very fascinating lecture. I think this is the first time I've heard you speak at length on this topic. I've myself missed probably some other previous lectures on this on some other occasions. So I think we were all very much aware of the elaborate town planning that the Harappans implemented, but we had never really thought about exploring this further and going into the nitty-gritties of town planning. So thank you for making us aware of this whole new dimension of Harappan civilization, and thank you for exploring it. So I will now take up some of the comments and questions in the chat box. I request the participants to type their questions in the Q&A box. It will be easier if all of them are together in the same place, and we hope to not miss any of them. So I will begin with a question by Shriya Anand, and she asks, why was the town planning and architecture so ahead of its times?
I'm not sure we can say that it was ahead of its time, ahead compared to what or whom or what other civilization. See, I don't think it's very useful to compare civilizations, because each of them, was great on its own foundations. If you look at the Egyptians and their pyramids, it's an astounding feat of technology and construction. There's nothing very comparable in Harappan cities, obviously. So we have to look at, what makes the individuality of a particular civilization rather than compare them. So I would not say ahead of their time. They had certain remarkable features like, extensive sanitation networks in the largest settlements. And very systematic organization of the different zones and so on. So I think this, exploring a civilization on its own terms is more fruitful than comparing them.
So the next question has already been answered, but probably if you want to add a few more comments, I will take this up now. So Shriya Gautam wishes you a good evening, and she also agrees that it is a fantastic study. She wants to ask, to what extent did the Harappan system of proportions affect the later Indian measurement systems of Hasta, Angula, Yojan, and the like?
So as I said, and I'll just briefly repeat, I believe there's enough ground to at least put forth the hypothesis. Ultimate proof will be perhaps never possible, but we will, unless we could get some major structures in the 2nd millennium BC, in the transition from Harappan to historical India, or rather, if you prefer, from the first urbanization to the second urbanization, there is a kind of a gap of almost a whole millennium, the 2nd millennium BC. So there were cultures, there were a lot of late Harappan cultures. There were other cultures like painted greyware cultures developing, and some of them developing into sizable towns. Unfortunately, we do not have much data like ground plans or extensive town plans or anything like that. So it's going to take time to, if we really want to prove the transmission, in just not have simple striking parallels, we would have to have at least a few structures in the 2nd millennium BC that would, for example, have the same proportions or be measurable with the same units. Right now, I'm not aware of that. If anyone listening here has any suggestions, they would be most welcome. So this is my brief answer.
The next question is by Shikha Rai, who asks, do you feel that before settling down at Dholavira, the people had tried to understand the landscape first? Because as we know, Dholavira falls under the earthquake-sensitive zone, and it is built close to the fault lines. So keeping these things in mind, they must have strategically built the whole city.
So this is a very interesting question. Part of it was answered by Dr. Prabhakar last month, where he explained that this, bracketing of the city by these two streams is clearly a definite design. It was, even if the climate was less arid than today, as seems to be the case, nevertheless, it was not abundant in rainfall. And therefore, the one thing that they immediately planned ahead of any construction and localization of the city was water management, water harvesting, water harnessing, water storage, and so on. So this seems to be the primary concern. Whether they were aware at that time of earthquakes is possible, because according to Dr. Bisht, one major earthquake struck in about 2700 BC, or at least before the full-blown, urban stage. And there is considerable evidence of destruction of some walls, and therefore they would have known that yes, it was earthquake prone. But this knowledge in this time, does it mean that they would expect such events to recur? This is very hard to say. However, there's a very, very interesting feature, which again is some potential study for the future, that some of the walls, the stone walls flanking the castle walls, the castle walls, the core of the castle walls is made of mud bricks. It is only the flanks of the walls that are made of stone. And both in these walls, as well as in the walls of the East Reservoir, and I remember standing on the edge of the reservoir and pointing out to this feature to Dr. Bisht, you find absolutely vertical joints. That is to say, instead of having different layers overlapping, you find that at some location, they don't overlap. From layer to layer, they are absolutely aligned. So you have one alignment from top to bottom, and it's as if two parts of the walls are completely separated. They are no longer interlocked. So I asked Dr. Bisht, I said, is that, when I saw I noticed this in the East Reservoir, I said, is that the result of restoration? Perhaps it can happen, reconstruction, or is it the original wall as you excavated it? He said, no, it is the original wall. It so happened that Professor Aryan, who is a very reputed civil engineer and structural engineer in particular, was with us. It was in 2009. He said, in structural engineering, this is called a fuse, because this is the weakest part of the construction. If you're going to have an earthquake, then there's a narrow strip of about meter and a half with these joints, complete vertical joints on either side. He said, then what is going to happen in an earthquake is that this part is going to fall off, and perhaps the larger parts of the wall will be saved. If you interlock your wall completely throughout, then perhaps the entire wall might fall off. Mm-hmm. So this was his hypothesis as a structural and an expert earthquake engineer. Well, we had nothing to say. It's very hard to prove again, but why should they introduce a definitely weaker feature in the wall construction if not for this? So this is just, I'm putting it to you with a question mark, and we have to leave it at that for the time being.
Fascinating. So there's a related question to this asked by the same participant, Shikharai. So having noticed all this, did you face any kind of problems while going through the statistical data? Because we know that Dholavira was constructed in different phases, and we have delineated, I think, 7 stages in the city, and people definitely repaired several of these structures, like the fortification wall. So in that case, how can we deal with the errors for the different phases of the constructions themselves?
Yes, so this question is absolutely valid. See, I discussed it to some extent in the last paper, which was published in Man and Environment. I really have to take this up again and supplement. See, there are different types of errors. One error could be that the Harappans themselves, while laying out, let's say I decide that I want this dimension and this ratio, but I may make a small error in measurement, or the mason building this may also introduce a small error. So initial error is one. 2, an error caused by, let's say, measurements by ASI. And I totally depended, except for 4 GPS measurements, which I did in 2009 with the help of MS Gadvi, a local geologist, a geologist from Gujarat. We did this measurement of GPS, so we had some additional measurements which confirmed the ASI dimensions. So there could have been a small error in measurement of these dimensions. So we are now going in the exercise of trying to confirm all the ASI dimensions and making them more precise using our 3D drone survey, which I mentioned at the beginning. Now, this is the second time of a possible error. Third time of possible error is introduced by this gap of 4,500 years, where, as I said, some stones may have moved a little bit, there could have been some tremors, there could have been some erosion, and therefore it's a third type. Nevertheless, it's remarkable that with all these three types of errors, and therefore I argued that if we get a good, match of a dimension with a multiple integral of a certain unit within, let us say, 2%, we should be reasonably happy. But I made it much stricter by imposing a 1% threshold. So I think altogether, taking these three types of errors into consideration and finding so many dimensions with an average margin of error of 0.6% all over the city, I think this makes it pretty certain that we can accept the ratios, and the unit works really very well. So this is a brief answer, but more in my last paper on the topic.
Okay, so the next question is by Christopher John, who asks, is there any evidence of a gnomon? I'm not sure what it means. It's spelled GNOMON. So is there any evidence of a gnomon being used, and what about other instruments? And I'll just briefly answer his next question, which is, will this recording be available? Yes, it will be. We do put up the talks a few days from now. We process the videos and we put them up on YouTube. So please go to YouTube and search for Professor Danino and IIT Gandhinagar, and you'll definitely find this talk.
So I'm not aware that, first of all, for those who might not know, a gnomon is nothing but a vertical stick, which will stand in classical times on some kind of a sundial, and the shadow of it is used to, for example, measure the east-west line. But this is a technique that will be evolved only in much, much later texts of astronomy during the early classical or late Vedic periods. And it can also be used, but with more complex calculations to even tell the time. So a gnomon, of course, there are some, wooden sticks, forget it, because wooden objects have not been preserved in the Harappan civilization. But there are certain objects of stone that are a little elongated. However, as far as I can see, they are not long enough, not thin enough to be used for such a purpose. They may have been pendants, they may have been all kinds of other things, weights, but I don't think there is a gnomon. As far as other instruments are concerned, the best candidate so far to my knowledge is a kind of a compass carved in shell, excavated at Lotal by Dr. S.R. Rao. It is visible in the Lotal Museum, and it has a kind of very interesting undulating shape, and the slots which are created by this undulation, the slots are very precisely 90 degrees and 45 degrees from each other. So you can measure out angles, if that was the purpose, which Dr. Rao tried to demonstrate, on a draftsman desk. He put this object and he showed the angles and so on. It is possible that this would have been used to measure out angles in the alignment of some streets, because some streets are perfectly 90 degrees or almost perfectly 90 degrees angles. So that is a possibility. Other instruments, just now, I pointed out to the rulers, the graduated scales, because perhaps some archaeologists will object if I say rulers, but they are graduated, and they seem to have been used for some scales. One, as I showed, was again from Lotal, the other was from Kalimangan. There is another from Harappa and another from Mohenjo-daro, but I've discussed them at length in one paper and showed that they perhaps were not scales. There is some kind of correspondence between all these units, but there are question marks, and I have discussed that in a paper. I'm not aware of any other instruments as far as I can see. Dr. Brian Wells did propose that certain pots whose volume he measured, pots excavated from several sites, were perhaps units of volume to measure out grain, for example. You see, in a market, if you're going to sell rice, you would need either to weigh the rice on a scale, but that's cumbersome. It takes a bit of time. So yes, scales would have definitely existed, and they've been kind of reconstructed by archaeologists, and you can see them in some of the books. In particular, I think Dr. Kenoyer's book on the Indus cities has a portrayal of scales, but it would be much easier to have a volume and have a standardized spot and measure it out quickly from a back and pour it out. This will be less messy. So this is the hypothesis of Brian West. I believe I have covered more or less all kinds of instruments that can be safely documented.
The next question is by Anirudh Bahuguna, who asks that he has read in your paper that the Harappans at Dholavira had absidial structures as well. So what could have been the importance of such structures? Were they sacred buildings or something else? And did they have any link with astronomy?
So astronomy, I can rule out for the time being, at least, because there's not been any study connecting it to astronomy. And it's, since we don't have, again, any Harappan literature, it's difficult to build any arguments as to their astronomical knowledge. Without going deeper into this, the building itself is peculiar because, first of all, it has very thick walls, it is apsidal, and at the center of it, there is another apsidal structure, which Dr. Bish, when he reported this structure in Indian Archaeological Review, he proposed that this was an altar. And he said that he found about 1 foot thick of fine ash in that structure. So fine ash alone would not probably match. I know that Dr. Prabhakar, who has joined us now, does not necessarily agree, but usually in any industrial use, you would expect to find some debris, some relics, some, if it is a kiln for metallurgy, you would expect to find some traces of slag. The problem, of course, is that this was towards the fag end of the Banawali excavations. And Dr. Bish did tell me that he would like to be cautious about this structure because he didn't have time to do a full proper excavation in minute detail. However, it cannot be ruled out that it would have been some kind of a temple, because an apsidal structure within an apsidal structure of very thick walls doesn't seem to be, first of all, either a habitation, and number two, if it's going to be for some industrial purpose, then it is difficult to define it. So anyway, I'm not categorical, but I think the temple hypothesis is as good as any other.
Okay. Saurav Lyle has 2 questions. So the first is that most of the Harappan towns have the same ratios, as you mentioned. So was there some kind of a technology mobility of the architect architects who were moving from place to place with this knowledge, or some chief town planner behind these?
So this raises a very deep question about the entire Harappan civilization, not just ratios, but all these standardized features that we see, whether weights or certain classical pottery styles, the seals themselves, the script, of course, and so on and so forth. Dr. Prabhakar spoke in some detail about this earlier. How were all these common concepts and practices shared in practice? So in this case, yes, we are concerning the question of town planners. How did they share these concepts? But it is the same for pottery. It is the same for weights and the seal makers and the craftsmen, because the craftsmen also shared certain common forms, like, for example, the carnelian beads across the entire civilization. So there's no easy answer to this, especially in the absence of the visibility of a strong ruler. There may have been a strong overall ruler, ruling over the regional powers, the regional chieftains, but he's completely invisible. He's not depicted anywhere as far as we can say. And therefore, there is a big question mark remaining there. To me, the simplest explanation is to take the community transmission of knowledge. Because in all traditional societies, not just in India, in all traditional societies across the world, let us say pre-industrial societies, technology has usually been transmitted via communities. You see, in Europe, you had in the Middle Ages, the Freemasons, they were a community of builders. And they shared those concepts, and we have a lot of literature on them. And yes, they were moving about. They were traveling from city to city to build a cathedral here or some palace there and so on. So the best way to transmit knowledge of a certain advanced type in traditional societies is to have a community structure, community organization. And we know very well how in India today we still have communities of stone cutters, communities of potters, and so on and so forth. So I think it is a very likely explanation, but there may have been other mechanisms over this also.
Okay, so we'll take the last question from the same participant. And I think this is in reference to, you spoke about the iron pillar. And and in the talk, you also talk about the distance between these two pillars that we saw in the picture. But what about the pillars themselves? Are they also in some kind of a proportion or a ratio?
Which pillars would that refer to?
He has asked about freestanding pillars in the town. And I think he's referring again to Dholavira.
This Dholavira, then we have a problem because you see, they are not monolithic. As Dr. Prabhakar showed us beautifully the other day, they are made of sections. There are pillar sections. Those sections were carved out in some quarries on the Khadir Island. At least one quarry has been identified, but there may have been a few more. And those sections, of course, had the advantage that, you know, for mobility, you didn't have to transport a 4-meter long pillar, for example, which would have been very heavy and therefore challenging to transport, challenging to erect. So all of this, of course, will be done in classical India. We will have huge monolithic pillars. For example, the Ashokan pillars are most of them monolithic. But here, the Dholavirans, if I may say so, found it clearly more advantageous to have short sections, like, you know, 60 centimeter to 80 centimeter high. And some of them, remember, were transported all the way to Mohenjo-daro and Harappa. And again, transporting a massive pillar would not have been so easy. Plus the fact that this gives you some advantages in precisely being able to adjust the height of your pillar. You can have a short pillar if you want, or a taller pillar, all depends on the structure you want to support. So I don't think we can speak of any fixed height of Dholaviran pillars in that case, no.
Okay, so I think that's about it. And in case I have missed some question, then I apologize for it. So there is one last question I see here by Anirudh. Maybe you can very briefly answer him. That again, he says in your paper you mentioned that they had the knowledge of both the true arch and the false arch, which we can see in Dholavira. So any comments on that?
It's not exactly like this. What I pointed to somewhere, I forget exactly where, is that, you know, the typical Mohenjo-daro well of trapezoid bricks is in fact what I call a horizontal true arch. Because if you put that, if you take half of the circle of the well and you put it vertically instead of horizontally, then you do get a true arch, because they are trapezoid and this will be structurally very, very strong. However, the Harappans, for all their inventiveness, didn't have that idea. And the arch they built, the vertical arch they built, was the corbelled arch, where instead you do not have a curve. You start with a certain, you know, width that you wish at the bottom, and then the next layer you will be bringing the stones or bricks closer and closer and closer until they touch at the bottom, and then you will have a key stone or key brick at the top. So this has some structural strength, and it is used extensively in the drains. For example, Mohenjo-daro drains have corbelled arches. So this is a good structure, but not quite as good as the true arch. In classical India, both the true arch and the corbelled arch will be used. The corbelled arch will survive nevertheless. So it's not a bad structure, but it's the Harappans did not know the vertical true arch. And it was, something of a joke when I spoke of the horizontal arch, which they conceived of for the brick wells. Yeah.
Okay. So I think that brings us to the end of the Q&A session. And thank you so much for patiently answering all the questions. Thank you to the audience, the participants, for staying with us till the end and asking such interesting questions. So I think with this, as I mentioned earlier, that we have more or less covered a lot of different topics concerning the prehistory and the proto-history of South Asia. And we will be moving on to some other important cultural phases of the subcontinent. So as I'm speaking, there are several congratulatory messages coming for Professor Danino. Thank you again to all the participants. And we hope to see you next month in the next talk of this series, which we will be announcing in a few days with a new speaker, a new topic. So, and we have been joined by Professor Prabhakar towards the end of the talk. He had to be somewhere else, so he could not be with us from the beginning, but he did join us for the Q&A session. So thank you, Professor Prabhakar. Thank you, Professor Danino. And with this, we close the webinar. Thank you. Have a good evening and have a good weekend.